She's a Senior Autonomy Engineering Manager at Uber Advanced Technology Group in Toronto, where she leads a team whose mission is to bring from research and into production cutting-edge deep learning models for self-driving vehicles. She received her Ph.D. in computer science in 2011 from the University of Toronto, specializing in machine learning, and was a visiting scholar at the University of Cambridge. She worked at Microsoft Research, Altera, now Intel, Kobo, and Kindred, at roles ranging from research scientist to VP, big data, applying machine learning techniques to various problem domains and taking concepts from research to production systems. She is an inventor of several patents and has authored numerous top-tier academic publications in the area of machine learning, computer vision, and computational biology. She is a regular speaker at AI events and is particularly interested in outreach activities for young women, encouraging them to choose technical career paths. For her volunteer efforts, she received the 2017 Arbor Award from U of T. In 2011, she was recognized as one of Canada's 50 inspiring women in STEM. She has been featured in Toronto Live, The Globe and Mail, 2ML and AI podcast, Rework's list of 30 influential women in Canada, in Canadian AI, U of T News, and other media ventures. The title of her talk today is Deep Learning for Self-Driving at Upper ATG Research and Development Lab. She will talk to us about deep learning for self-driving, and she will cover some of the recent advancement from the Uber Toronto lab and their approach for taking it into production. So I would like to invite Inmar to the microphone.
Thanks. Thanks, Dragos. All right. Okay. I can go around and you can still hear me? Awesome. Thanks for coming. I have a little bit more time than our previous speakers, so I'll try and talk a bit slower, but I do get excited and then I talk fast, so we'll see how it goes. So I want to tell you a bit about the stuff that we do at the Toronto ATG lab. We have a lab where we are developing technology for self-driving. We are in the Mars building, which probably a lot of you know. It started 2.5 years ago, so Raquel Urtasun was a professor at U of T and also a Vector Institute co-founder, was kind of poached by Uber to start a self-driving lab. She's been working in the space of self-driving for a while. So she brought her research team, and that was 2.5 years ago. Now there's over 60 people in the lab. A lot of them do fundamental research in the areas of AI, computer vision, and their application to self-driving. What about myself? So I oversee the engineering for research. So my sweet spot, the thing that I like to do is to take really exciting scientific ideas and bring them into production system. Okay, we heard a little bit about what I did, so I'll skip over that. I want to, there's a lot of hype around machine learning and deep learning, so I'll take like 3 minutes to talk very briefly about what machine learning can actually do and can't. So it's not something where you push data and magical ponies come the other side. It doesn't answer any question that you might want to consider that is interesting or difficult. If you know how to program a supervised learning algorithms, and specifically the variants that we see nowadays in production systems like deep learning algorithms, or it's a function, okay? It's a function, which means that it has a well-defined input and a well-defined output. If you can't state your problem in terms of here is what I want to input to the system, and it's like computer specific, and here is what I can expect to get out of it, which is not insight about the data, right? It's like something very specific, then it's probably not going to be a machine learning algorithm. And the second thing you need is a set of data that shows the correct correspondence, usually annotated by humans, between the inputs and the outputs. Okay, so on to self-driving. So self-driving is a very exciting problem. I think we can all agree on that. Once upon a time, we trained horses to take us from the bar where we got drunk to home, and now we can train, cars to take us or our horses from the bar home. It's also very important. It's important because about 1.2 million people die every year from car accidents. And we think that eventually, not now, eventually we're going to be able to help with that, because machines do not drive under the influence. They don't get tired. They don't get drowsy. They don't get distracted by the kids fighting in the backseat. They're just going to drive no matter what. It will provide things like mobility for people who are not able to drive themselves, so like the elderly or the disabled. My grandfather, who is 88 years old, talks to me about once a week, and he asks me once a week, so are you making progress? So I'm under a lot of pressure there. It will help, I believe it will help congestions in cities, and especially the combination of, and this is why I do believe in the Uber mission, so the combination of electric cars, self-driving, and specifically ride-sharing, so not everyone owning a car, I think is going to be pretty impactful. Right now, the average car spends about 95% of its time being parked, okay? That's a lot, and that's a lot of space for something that is not really doing much most of the time. And eventually, when we have these networks of self-driving vehicles, we can also use techniques, not necessarily from machine learning, but just optimization theory to make sure that we have the right amount of cars in the right areas so that we can move people around effectively. And that will lead to less congested cities where we can reclaim some of the public spaces, less pollution, more space for us. So it's also really, really hard, okay? let's not get confused about that. So let's look at this video. So in the middle, we have the self-driving car in purple, and then we have a whole bunch of other actors. Actors is the generic term we use for things like vehicles, and it can be cars, trucks, motorcycles. We have the little dots here represent pedestrians. And you can see that there's just a lot going on. There's cars passing the car. There is intersections which are complicated. There is pedestrians that can at any given moment do whatever they feel like doing. So even in a world where all the cars are self-driving and obey the traffic rules, we will still have pedestrians and interactions with them. And so the car needs to be able to account for all of this complexity and understand everything that's going around it in order to drive where it needs to safely. So how are we going to approach the problem? Well, first of all, the car needs to understand the world around it. It needs, just like us, sensors. And this is actually our newly minted cars. For those of you who follow tech news, we announced, I think about a month ago, our next generation of self-driving fleet. So they used to be gray, now they're white, but there's a lot else that changed in terms of the sensor suite. The compute on board, and so on. The most important sensor that we currently have is this thing on top, the LiDAR. So this is basically a laser array. It spins 10 times a second, and it sends out laser beams. It collects them back, measures the time of flight, and this is how we know how far things are. Okay, we don't know what they are, but we know how far are things away from the car. So it's a depth estimator. We also have Rgb Camera, so there is a whole array of cameras mounted also at the top that allow us to see the photonic information, but of course we don't know how far things are. We also have radar, proximity sensors, and so on. And then we have, at the back of the car, there is a big compute unit. There is a lot of specialized hardware. We use GPUs. We use FPGAs. It generates a lot of heat. There is a whole cooling system. So it's quite a complicated beast. And what does it give us? Fundamentally, it tells us what's going on around us. This is a view of the front camera on the left. And then on the right, we have a projection of the LiDAR imagery. So LiDAR is three-dimensional. It's hard to look at it and understand what's going on in general. But specifically, what we're doing here is we're projecting all of the information as if we're looking from the top down. So this is called the bird's eye view or top-down view. So this, let me show it again. Let's see if this works. Yeah, okay. So, so you can see the self-driving car is in the middle, and if you squint your eyes and kind of, imagine that you're looking from above, you will see that there is shadows being cast. It looks like shadows, and basically the car is in the middle of the road, and you can see a little bit of information about other cars passing it by, or pedestrians, and then on the side are the buildings. This is one way of looking at the LiDAR information that we do a lot of our processing in. And the reason that this looks kind of like a snow angel thing is because the car itself occludes some of the information. So these are basically the occlusion coming from the mirrors or these big floppy ears thing. I realize this is kind of like, medical images. Until you spend a lot of the day staring at these things, they don't make a lot of sense, but this is like our bread and butter, so we're pretty used to it. So we take this information, we take the camera, we take the LiDAR, that's our input. What is our output? Our output is basically steering commands, so right and left to the wheel, and then acceleration and deceleration, okay? That's driving, essentially, taking sensory information and translating it into steering, acceleration, deceleration. What happens between the sensors and the controls, so the controls is the steering, sensors is the information, is what we in the self-driving world call autonomy. Autonomy is the brain of the car, as it were, and it's solving the problem of how do we go from this one input to the other output that we're interested in. And traditionally, people kind of divide it into a pipeline system where the first thing you do is you deal with what we call perception. Perception is the problem of where is everyone that I care about in the scene. So where are the pedestrians, the cyclists, the motorcyclists, the cars? Where are they headed? How fast are they moving? Okay, so it's understanding the dynamic nature of the objects around me. Once I know where everyone is and how fast they're moving, I can predict where I think they're gonna be in the next time horizon. So maybe in the next 100 milliseconds, in the next 2 seconds, in the next 10 seconds. Of course, the further out I'm trying to predict, the less accurate it's going to be. So prediction is the task of where is everyone going? And then once I know where everyone is and where I think they're gonna be, then I can motion plan. I can decide how do I execute I. So when I say I usually mean the self-driving car, very strong identification with the robot. Where am I, how am I going to plan my own motion so that I get where I wanna go in a safe way, in a comfortable way for the rider, without violating any of the traffic laws, okay? So that's the motion planning. And once I've solved that problem, so I know where everyone is, I think I know where they're going, I think I know how I'm gonna get to where I need to get, then I can send the command to the controls. Let's look at it from like alongside the data. So the sensors, this is the sensor information, the LiDAR in bird's eye view. And I also can use, there's one thing that I forgot to mention. Underneath all of that, I've put this blue line that says AV Maps and Localization, AV Autonomous Vehicle. Most self-driving platforms that are meant for full-on self-driving, like the one we're trying to develop as opposed to assistive technology, rely heavily on very high-definition maps. So these are not like Google Maps. These have a lot of information, a lot of three-dimensional information about how the scene looks from the perspective of, say, a LiDAR. Also where all the lanes are, so the specific lanes in the road, where all the stop lines, intersections, crosswalks, and so on. So these are AV maps. And most of these platforms use something called, they employ localization. So localization is the problem of, given my sensor reading and giving these high definition maps, where am I on this map, okay? This is kind of like GPS on your Google map, except it's, GPS will give you maybe 10 meters of accuracy. Localization for self-driving needs to be at the resolution of 5 centimeters, 5 to 10 centimeters. Why? Because if I'm more than 10 centimeters to the left, I might actually be in the next lane already, right? So that's the level of localization we need to be able to do. And the reason we want to localize is because it makes the driving problem easier, because now I know where my intersections are, okay? I don't need to figure everything out all the time. I'm using my prior knowledge. And then I just mentioned that we have also the whole, the framework that this thing sits in terms of, this is a robotic system, so you have to design some sort of a software system on which you can run these different processes, these different sensor processing information, and so on, and the compute power that you need in order to process autonomy, which, given the amount of deep learning techniques we use, is quite a bit of compute that you need to run on the car. So everything has to run on the car, because we can't send it to the cloud, and this day Amazon has some problem with their services, right? And it has to be, you have to not rely on any type of latency that has to do with communication bandwidth. So the computer has to be on the car. Okay, so we have the sensor. Here is the sensor data. Here is the map data. So you can see that we can see exactly all the lanes, the intersection information. And then this is the detection. So the detection is part of the perception problem. Where is everyone? So I'm denoting here that I've detected my pedestrians by yellow, my other cars with the blue rectangles. And then tracking is the detection over time. So every time I spin the LiDAR, I try to detect everyone in the scene. But I want to know that this detection from the previous frame and the current frame are the same detection. This is called tracking, right? Over time, I know that these detections actually are the same car. Why do I care about this? Because that helps me estimate things like the velocity, right? I can look at historically, this is the one car. It's moving at this particular rate, which I can now calculate, and now I have an estimation of the velocity. And then prediction is basically, as I said, where are these cars going to be? So based on the historical information of the velocity, I can now do the prediction. The way that we're denoting it here is by drawing these points. So the points are telling me where the car is going to, where I predict the car to be in the next 100, 200, 300 milliseconds, and so on. So this is, I think, about 3 seconds worth of prediction. And you can see that we can also predict the pedestrians. And then planning. Planning is basically, as I said, estimating what the trajectory of the self-driving vehicle in blue in the middle is going to do in the next time horizon. Here it's just going to go forward in this particular velocity. And then we send it to the controls. Okay, so how do we actually solve this problem? So let's compare traditional engineering and end-to-end learning. So I said in the beginning, machine learning, input, output, well-defined. I can give it examples, right? I can go and drive for thousands of miles, and that becomes my label data. So let's start with the end-to-end learning, actually. So it's simple and easy to train. It doesn't actually, if you have the data, you can shove it into a neural network, and you'll learn something, and you'll create very fast a very nice demo. But it's not really going to scale to a lot of the edge cases we see in real life, because you need so much data if you're going to have the system as it is, as an end-to-end learning system, try to account for all of the complexities of learning, of driving. It's hard to interpret, right? So we don't really know what it's learning if we're just trying to create one network that does sensors to controls. A nice thing about it is that we are propagating the uncertainty. So we're not making hard decisions along the way and losing information along the way. We kind of always keep in mind the different interpretations of, say, our detections. Maybe I'm not exactly sure that this is where the pedestrian is, and I can carry forward this probability around the actual detection. It's optimized for what we're trying to actually do, which is drive like humans. It's hard to incorporate prior knowledge. So by that I mean you can't tell the network explicitly, if you're doing this end-to-end learning, to not collide with other cars. It's going to figure that out by never seeing it in human examples. The labeled data is easy to get. We just need to drive around. And we're sharing our computation across all of the things we're trying to do, so it's fast. Traditional engineering is this pipeline system that I just showed you. So first we do perception. So we detect where everyone is, we track them. Then we do prediction, and it's a separate process altogether. So we've made some hard decisions, we moved on to prediction, and then we move on to motion planning. So on the one hand, so this is how people have treated it prior to, say, introducing machine learning into self-driving. The problem is it gets very messy. You have this very complicated system. It has a lot of moving parts. Every time you change one algorithm in the beginning, you need to retune the rest of the system, because people have hand-engineered a lot of hacks and a lot of adjustments that are very specific to, say, the detection algorithm. What you do get, which is nice, you get interpretable intermediate steps. So you know these are my detections, because the detection algorithm spits the detections out, as opposed to the end-to-end neural network, which never told you anything. It makes these hard decisions. So once I'm done detecting, I'm done detecting. I can't go back and say, well, I wasn't actually 100% sure about this detection, and now I can propagate this uncertainty. We're not optimizing for the right problem. So even if I build a neural network that does my detections, so okay, I'm using neural networks, what I'm going to measure is how well did the network detect the objects in the actors in the scene. And the problem with that is this is not what driving is about. In driving, for example, we don't pay as much attention to the cars that are very far away. we don't pay as much attention to the car behind us that are moving in the opposite direction, because we know these are not very likely to interfere with us. But if we're just measuring accuracy of detections, the algorithm is putting just as much computational power into figuring all of that stuff that's not interesting as it is to the stuff that's interesting. So fast-moving objects that are right in front of us. And it's not trivial how to incorporate that prior knowledge easily. It is hard to get label data. You need, if you want to build a detector, you need to have someone draw these little squares around each one of the cars and the pedestrians in the scene. Otherwise, you're not going to be able to train any algorithm. And you're computing things in this pipeline where you're not sharing computation, so it's pretty slow. So one of our big principles in the lab is that we want to move towards end-to-end learnable, interpretable driving systems. So on the one hand, we want to build this one big neural network that goes from sensors to controls. On the other hand, we want to be able to understand what's going on. We want to understand, we want to incorporate prior knowledge. We want to get all of these benefits that the engineering systems have. And so we kind of want the best of both worlds. And in the lab in Toronto, we've been kind of slowly driving into this solution by building the subcomponents and kind of growing and growing the capability of the network and combining them together to arrive at this type of vision for how to solve the problem. So one of the first algorithms that was developed in the lab is basically combining together the perception and prediction. So it's one neural network, it does perception and prediction, but it does emit in, the intermediate results. It does tell you where all the detections are. So this is a paper from CVPR 2018 called Fast and Furious. The algorithm is very fast. And so what you see here is every square is basically a detection of a vehicle. The color coding along the frames indicates that we're doing tracking. We're able to associate across frames correctly. The number of top of the car is an indication of how confident the network is. And then you see this prediction, so the waypoints, these points emitted from the car indicates where the algorithm thinks the car is going to be in the next time horizon. The next thing that we wanted to do, building on top of that, is to not just have these continuous predictions, which are basically trajectories. It's like a numerical representation of where the car is going to be as some sort of a curve. We want to actually be able to reason about high-level actions. So we want to be, and what are high-level actions? We want to be able to predict that the car is stopping, is about to change lane. If it's changing lane, is it to the right or the left? If it's turning, is it to the right or the left? So now on top of the previous network, we're emitting some more outputs, which are these types of predictions. So now it's more like classification as opposed to just regression problem. So you can see that we can emit the probability of its being of stopping and being parked, and then these errors. So we're looking at the bottom. Sorry, these errors are indications of the prediction of whether the car is going to stay in the lane, change to the left or the right, so that's the 45-degree angle, or take a turn. So you can see the car now here, so the algorithm is predicting that it's going to turn left. Okay, in the interest of time, I won't go back to show you some predictions that are successful, but this was the next level. More recently, so CVPR 2019, this is a month and a half ago, we showcased this neural network, which is an end-to-end interpretable neural motion planner. So this now takes us, let me jump forward. This is one neural network that does perception, prediction, and motion planning. And it does it in an interpretable way, so we know where the predictions are, we know where the detections are, we do the tracking, we know where the predictions are for each individual car. But we also, at the end of the day, we have a motion plan, which is based on, it's a bit, there's a lot going on here, but these color bubbles basically represent where is a good place for the car to be. Okay, in the next 100 milliseconds, 200 milliseconds, and so on. And based on that, we can sample a trajectory from this volume of good places for the car to be. And by good, I mean with respect to what's going on around it. And you can see that every once in a while, good and possible, every once in a while, these things will split, like now, indicating that there is the possibility of turning here. and it wouldn't be such a bad idea, but it's better to keep forward. This particular model still does not know about routing. It doesn't know where we actually want to go. It's basically saying if I put a car on the road and it has to go somewhere, where should it go? So the routing is the next step. And then you can basically, here you can see it splitting into maybe staying in the lane or going to another lane. These are all valid choices where you can drive around without hitting other cars. So this is a very recent result, and it's demonstrating the ability to come to this end-to-end style of learning, or almost end-to-end style of learning, but with all the benefits that we wanted from the more engineering style of solving the problem as a pipeline of systems. So that's one aspect of the technological vision that we're driving towards in the lab. And there's a typo here, but then I want to show you some more cool stuff that is being done. One of the interesting problems, so I showed you only LiDAR-based algorithms up until now. One of the interesting questions in general in the field of sensor data is how do you fuse sensor data? So you can be very naive about it. You could say, okay, I have my cameras, so these are RGB values. I will, dump them into the network as an RGB style input, and I can take my LiDAR and I can put it in top-down view, and then I can just take these like as images and push them into the network. But I'm losing a lot of my prior knowledge about how these things are actually related to each other. I am unable to do things like look at the image. So if you know a little bit about architectures for understanding images, a lot of times you do things that allow you to see things at different resolution, right? By basically convolving, getting a smaller image and connecting the features on your prediction side. So you can't really do that if you're just throwing all the information. You lose the relationship between the LiDAR representation and the camera representation. The LiDAR representation is also top-down in this case, and the camera is looking at it that way. So this is an algorithm that, again, from about a month and a half ago, which shows one clever way of combining this sensor information in a way that allows the network to keep the relationship between the LiDAR and the images. The sauce of this is in the paper if you want to read more about it, but what you can see here is basically the predictions, and notice that the predictions on the camera are three-dimensional. So in regular RGB, you can't really do that. You don't know where the volume is, you don't know where the distance is, but now because we have the LiDAR information, we're able to back project it into the image and have a sense of how far things are even in image space. Another thing that we care about when we try to predict motion, when we try to predict where cars are going, is actually changing lanes. And even though not all people use the turn signal, some of them do. And when they do, it's very useful information. It's very useful information because it allows us to know that a car is going to change the lane a long time before it's actually doing that. So it allows us for safer, better predictions. And so we have a module within our stack that specifically learns how to detect turn signals and be able to reason about which turn signal is turned on, where is the car going to go, and that is incorporated into the pipeline system in order to better predict. Another problem, another way to look at sensor data that is very different from these detections I showed before. So the detections I showed before were just trying to say where are all the different actors in the scene, and we represent it by these bounding boxes. But we're not really accounting for everything. And if you really want to understand everything around you, you need to account for each and every pixel. So the machine learning task or the vision task of accounting to each and every pixel is called segmentation. Okay, and then there is instance segmentation and semantic segmentation. Semantic segmentation is being able to associate a semantic label, so a car, a tree, a house, a person, and so on, to every pixel. And then instance segmentation is when there are actually identifiable cars. So I don't just want to label all the cars in the scene with the same label. I want to say, okay, this is car number 1, this is car number 2. I want to be able to account for it at the instance level. And I want to, and doing these things together, both the counting and just the semantic segmentation, has again been a task that people were not quite sure how to combine together into one unified network. So again, a month and a half ago at CVPR, we presented UPSNet, which is a unified panoptic segmentation. So panoptic refers to the task of doing the two things together. Why doesn't it run? Oh, okay, sorry. This is much more interesting. Okay, so you can see that, and there is no tracking here. This is run on frame by frame with base, and we're not indicating with color the different instances. So all the cars here are blue, but you can see how well the network is able to reason about every pixel, pedestrians, trees, signs, and you can use that. So, you know, what can this be used for? For a lot of different following tasks, but one of them, for example, is now I know that this is a traffic sign, and so if I'm running some sort of an algorithm to understand what is this traffic sign actually doing, I know to concentrate only on this region in the image. And in general, it gives us a much deeper understanding of the scene. The task of semantic segmentation or instance segmentation, I showed it on RGB. You can also apply it for LiDAR imagery. So LiDAR is much more sparse. You can still associate every LiDAR point with a particular semantic label. So in this case, we're seeing a comparison of the two algorithms. So the top is the ground truth, the bottom is the algorithmic prediction. And again, it's a little bit hard to see if you're not used to it, but you know, you can see some cyclists on the top here. There is trees, there is the road. So here we're segmenting both the static and the dynamic element in the scene. And for every LiDAR point, we're saying, is this the road? Is this the sidewalk? Is this a different car? Is this a pedestrian? And so on. When we want to move beyond the need to do this localization that I talked about, so localization is right now the way that a lot of these self-driving systems work. But there are a lot of drawbacks. You need to map extensively any area that you actually want to be driving in. And then if you lose localization, if you lose your pose, if you don't know where you are on the map, you're suddenly blind, right? So even from a safety perspective, we want to be able to do things like be able to drive and maybe safely stop if we lose our localization, if we don't know where we are anymore. In order to do that, you want to understand, for example, where the lanes are. So in this system, we have, again, combined input of the camera imagery and the LiDAR. And the task of the neural network here is to predict where the lanes are. And once you know where the lanes are, you can basically just like, let's just keep driving in this lane until we find a place for a safe stop. It's hard to see, but on the left is the middle is the ground truth, and the right is the network prediction. And here we're just projecting it into the image so that it's easy to visualize it. And you can see that the network, definitely when it's just a road, like a simple road, it can do very well. And then one of the challenges for a network like that is how to reason about ramps and understand what's going on, because you don't see a lot of the data. Even if you're driving around a lot, there aren't a lot of on and off ramps. So I'm at time, I think, almost. The last thing that I wanted to very, very briefly mention is to take all of that stuff and put it into an actual car takes a lot of effort that is beyond just working on the core algorithms. So we have our research team in the lab, they work on these core technologies, and then there is the team that I lead, and we do a lot of, okay, we have this algorithm, it's a really nice paper, how do we actually make sure that it's running correctly inside the production systems and recovering the same types of results? What happens at not just the model level metrics, but the end-to-end system? Does it still provide the same type of performance that it promises at the model level? How do we train it within the system? How do we do inference at less than 100 milliseconds per frame, right? Because we need to process these things 10 times a second. And what are the tools that we have in order to get to inference that is that fast on the GPUs? We work a lot on fast training frameworks for deep learning algorithms. So how do you do distributed deep learning, GPU-based training at scale? And then how do you look at metrics, define metrics, and test the system so that you know that it's not just doing well for the particular model that you're training, but also at scale with safety, with something that is convenient for the rider experience and so on. So with that, I have a few more minutes for questions. Thanks for listening.
Want some questions from the back?
Great talk. So can I have two very quick questions? One is that, like, how do you do the road conditions? So, like, if you have potholes or if there are, like, I don't know, the surface is not very smooth, does it detect your system those things? And the other thing is sometimes the decisions are not between good and bad, or between good and better, or between bad and worse. And do you have metrics for that to see, like, if you're making the better decision?
So for the actual road conditions, so some of the road conditions are so bad that they end up in the map, right? They end up as part of what you know about the world, because this big pothole is always there, and then the information is around. One of the challenges is how do you adjust to changes in the road condition, and it can be the road itself, it can be things like construction. So construction comes and goes sometimes in a day. With a construction, you have a guy standing with a stop sign, right, turning it around. So understanding this is quite a challenging aspect of self-driving, and at least the approach right now is that we need to treat it as a separate problem of its own, and we build a technology around these types of road understanding. As for your second question, so ultimately you need to define what you're optimizing for, right? And especially around the motion planning side of things, this is where you say, I need to be able to create a plan for motion and then evaluate it according to some cost. And the cost can include whatever you want it to include. So if you hand engineer it, as is traditionally done, then you can say, okay, I want to pay a certain penalty for accelerating, and the penalty might be quadratic in terms of how much acceleration I put. I want to put a huge constraint, like an infinite penalty, if I'm hitting, the curb or something like that. So, so traditionally, people have designed these metrics, and then you basically evaluate, and this tells you the bad and worst, and you're just trying to optimize for the for the bad as opposed to the worst. One of the things we're trying to do is to learn that from human examples, and so basically trust that humans are going to give us the best type of example. But these, okay, I'm seeing your face. These are not any humans. These are trained drivers that are trying to drive as safely and as well as you possibly can, respecting all the rules of the road, which interestingly, as soon as you sit in a self-driving car, so the self-driving car is not allowed to violate traffic laws, right? And that helps you realize very quickly how many times we violate traffic laws as humans without even noticing. So I'm not talking about, taking that, amber light when you know you really shouldn't. I'm talking about things that we do all the time and we don't notice. Especially one example is we have a car parked on the side of the road. There is a non-dashed separator between the lanes, and we just nudge into the other lane, okay, to be able to pass the car. The self-driving car is not allowed to do that, and it knows it's not allowed to do it. So that's where we have things that, this is when we have the self-driving car basically making this sad noise, kind of like a Roomba, and saying, I don't know what to do now, because I know I can't solve this problem. I can't, drive into the car, and I can't nudge.
Thank you for the talk. I have a question regarding the tracking. Here.
Okay, yeah.
How far ahead of the cameras do you keep track, and how far behind you do, such that the memory does not get overloaded with too much information?
So you're always limited you're fundamentally limited by what you can see, which is always at the range of several hundred meters front and back, right? You want to be able to account for occlusion, which means that, I've detected some car, and now I've detected, let's say, 2 cars, because I can see one of them just like, I can see half of it, and now it's moved, and now I don't see it anymore. So from the current frame, I don't know that it's there, but I can retain a memory, and I can, if you know a little bit about networks that have a sense of memory, so you can use something like that to basically say, I still think that there is something there. In terms of for how long you can do it, it depends on how much capacity you want to put into being able to remember it, and it usually translates to something in the order of seconds.
Hi, I come from aerospace industry, and I'm wondering if there's any work done on the redundancy aspect, like what do you do in a degraded mode, and also so how do you plan on actually making this productionizable? Like, is it going to be a fully integrated system, like an embedded system, one supplier, or like how do you plan on integrating all the different suppliers, picking the suppliers, like coming up with requirements, integrating that into a single solution?
Yeah, so there is a lot of parts to your question. Let's see if I remember all of them. So especially after the incident a year and a half ago, ATG really dove deep into the whole area of safety. Okay, so we've ramped up our safety to be, it's an independent body within the organization that's only concentrated on how do we ensure safety. Some of the ways we attack it is, so we do have people from the aerospace industry and people that come from industries where there is like strict restrictions on safety, and we use the same types of thinking. So for example, there is a completely independent separate system in the car that is, it's got its own power supply and all of that, and all that it has to do is it's a collision avoidance system, right? So it's not as intelligent, it doesn't understand as much as these other algorithms, but it knows when there is something that could be a collision risk, and it responds to that, and it will override the main system. There is a lot of policy type groups that are between different companies in the space, between the self-driving companies and the governing bodies at the city level, the provincial level, the federal level, where we're trying to set up the rules. Actually, Uber released a few weeks ago our guidelines about how to do safety, and we're the first in the industry to kind of put out a white paper that describes our approach to safety. Simulations, there is just a lot of things. The testing that we do, in order to take any piece of code to the road, there is the model level testing, the system level testing, subsystem, system, end-to-end testing, simulation of various types, and then you take it into an internal track. So we have in Pittsburgh this basically fake city. It's kind of fun. And you drive around in the car. We put it in all sorts of test scenarios. So we basically have these, mannequins that are, they go into so they kind of simulate a pedestrian jumping into the road or someone opening the door of a car. So there is a lot of these fake scenarios, fake in the sense that you won't see them day to day when you're driving, but these are the things that we need the system to still be able to account for. And that's, if you don't pass the series of tests, the code is not going to go into production, no matter how good the detections are, for example.
Okay, let's have one more.
Well, I didn't know I'll get the mic. Okay. Oh, no. Okay, the one question I have is that when we look at the system here, it's like most of the calculation, everything that happens is happening in the car. But are you guys working on communicating with other vehicles wherein it will help in computing faster and
yeah, so it's definitely one of the most exciting approaches and ideas for how overall we can continue to develop this technology forward. And I can't tell you any of the specific details because the publication is not out yet, but we're definitely working on it, and we have some very exciting results. And again, the scientific question here is, what do you communicate? Because there is a lot of sensor information. It's not effective to communicate the whole thing. What do you communicate so that the problem formulation is, what do I communicate so that the other cars benefit the most from this, this limited communication bandwidth, and how do you show that actually the driving overall is improved? So stay tuned for that.
Okay, one more, and that's it.
Thank you. My questions for you is, when the autonomous go on production, what do you see the adaptation over time in terms of the big city like Toronto, and you know, just kind of general future outlook?
I think it's a hard question to answer because it's a lot of speculation. To me, one of the interesting aspects of this problem is it's going to get harder and then it's going to get easier. So, which is not very typical. And the reason it's going to get easier is because you'll have more and more self-driving cars, and when you know that the other car is self-driving, you can communicate with it, you can expect it to obey all the traffic rules, you can put a lot of trust in what the other cars around you do, but before we get there, we're still going to have this mixed population of human drivers and self-driving vehicles where you can't make any of these assumptions. So, you know, in a world where you only have self-driving car, the problem is much easier than it is right now, but we're gonna have to first, you know, ramp up before we can ramp down. I'm not like a, you know, I'm not a futurist. I'm more of a technologist, so I don't know what it's actually going to look like, but I think it's going to be pretty exciting. Yeah.
Okay, thank you very much.
Thank you.